Okay, so for this week and the next week, we're gonna jump into topic of graph theory. So a very natural question to ask is, for a mathematician, what is a graph? So most of you guys, when you think of a graph, are probably thinking something like a pie graph or a bar graph, or maybe uh, kind of a series of data points um, that are arranged like this. This is not what we are talking about. In math, a graph visually is basically a bunch of dots that we call vertices, or sometimes we call them nodes, but generally we call them vertices, and edges that connect those. So this would be a graph right here, or this would be a visual representation of a graph. And so if we name all of these vertices, T, these are actually the same graph. These are two different visual representations, but they represent the same thing. They've got the same underlying structure, so we consider them the same graph. On a strict level, a graph is a double of a set of vertices and edges, where the vertices are are what we would represent as these points, and the edges are generally represented by the names of the two vertices on either end. And then sometimes we can include a number because we could have something like this, what would be called a non-simple graph. If there's multiple edges connecting or two vertices, if there are multiple edges there, then it would be considered a non-simple graph. But so this is like the strict way that we define it, and that's why we can say that these two guys are equivalent, because they have the same underlying. They're defined by the same set, but they are just different visual representations. And usually, if we have a good understanding of the visual representation, that's going to be enough. So another example, this guy right here is called K4. It's the complete graph on 4 vertices. This guy right here is also K4. So these are the same graph. They're just different visual representations of the same graph. And this is a kind of very different visual representation that doesn't have any edges crossing each other. But they do represent the same underlying graph. So K4, I said these guys are both called K4 because they're the same graph. K5 is the complete graph on 5 vertices. And then we get a star on the inside. Cool. K6, so complete graph meaning that every vertex is connected to every other vertex. So this guy is connected. So 1, 2, 3. Vertex 1 is connected to 2, 3, 4, and 5. vertex 2 is connected to 1, 3, 4, 5, etc. And up here, if we were to number these guys, we would do 1, 2, 3, 4, 1, 2, 4. 1 is connected to 2, 3, and 4, 2 is connected to 1, 3, and 4, 3 is connected to 1, 2, and 4, and 4 is connected to 1, 2, and 3. So that is, when we say a complete graph on n vertices, we just mean a graph where all of the n vertices are connected to all n minus 1 other graphs. So each vertex has degree n minus 1, meaning it has n minus 1 edges attached to it. Another important cluster of graphs is the cycles. So C6 would be 2, 3, 4, 5, 6. C5 will look 1. It's just a graph of 5 vertices such that each vertex is connected to one vertex on each other side of it. So that forms a cycle. So you can start at vertex 1. So you can start at any vertex, and then you can go around touching every single vertex exactly once by just keep on going through the only other option. Another one is, let's say, K32 as the example. So 1, 2, 3. So this is the complete bipartite graph on 3 and 2 vertices. So bipartite just means that there's 2 sides of the graph such that vertices within one side don't touch each other. So 4 and 5 don't touch each other, 1, 2, and 3 don't touch each other. But yeah, so these guys form one side of it, these guys form the other side, and that's but the 4 and 5 don't touch each other, 1, 2, and 3 don't touch each other. We can also draw this so that there are no lines crossing each other. If we just do that. So this is an equivalent graph with just a different picture representing the same graph. Give you another example. I'll do K34. You'll usually, this was a little bit unusual. You usually write the smaller one first, but it doesn't matter, but it's just how it normally gets written. Wrong side there. So 1. And 1, 2, 3. So this is another complete bipartite graph. This one cannot be written such that none of the edges cross each other. We are stuck with it as is.